Yet most manufacturing is based on breaking these complex structures down with chemicals and high temperatures, only to rebuild them into everyday objects. But what if we could turn this around? The EU Horizon project, BioUPGRADE, is pioneering an effort to leverage the power of nature to create new biomaterials by upgrading the natural resources instead of degrading them.
We're opening a new paradigm shift on how to use lignocellulosic fibers. We really want to utilize the excellent assembly and structure properties of the biopolymers in biomass intact as they are.
And be smarter with the way we can convert these existing materials into textiles, into packaging products, into personal care products.
Scientists in Finland, Spain, and Sweden are collaborating in the pursuit of improving biomaterials development by creating new circular processes using nature's own biological catalysts, a group of proteins called enzymes.
Enzymes are nature's catalysts. They introduce a functionality into their substrate, and then they can repeat that action many times without modifying themselves.
Enzymes can be found in all living cells. Although they have been put to industrial use for decades, enzymes have primarily been used for the degradation of biomass.
Normally, enzymes, they are used to hydrolyze the biomaterials, but in this case, we try to keep the material as intact as possible so that we just open the structure and give a better reactivity.
Compared to synthetic catalysts, enzymes offer reactivity in water, high selectivity, and they can operate in mild conditions. They can also be optimized through protein engineering, but traditionally, they're considered costly. However, scientists have discovered a new group of natural proteins called expansins that have potential to aid biomass processing.
These proteins are non-hydrolytic proteins, and they are fungal expansin proteins, and we use them for enhancing the enzyme's activity.
Another benefit is their inert nature.
These proteins don't add new chemical functionality into fibers, but they add new mechanical properties into fibers. We don't know exactly how they work yet, but expansins, what they do is they disrupt non-covalent interactions between neighboring fibers, causing the fiber to then swell. And this is an example of cellulose activation. And that process is really important for dissolving cellulose in a way that lends it to spinning, an important first step to making sustainable textiles from wood-derived cellulose fiber.
While nature can provide us with expansin-like proteins, the scientists at CIC BioGuine are not stopping there. Using powerful computational tools to accelerate enzyme optimization, the scientists in Spain are conducting ancestral reconstruction to resurrect ancient proteins. In other words, reverse engineering evolution.
Quite often, those ancestors show interesting properties such as improved functions, improved efficiency, improved stability, which are the basis of the new biocatalysts that we are actually using in the project.
Professor Perez Jimenez's team is exploring the vast potential of these ancient proteins.
Ancestral enzymes are like a Swiss Army knife. They're not that specific, but they can do a lot of things. We use them as a tool to create new materials.
Besides expansins to improve the physical properties of natural fibers, the BioUPGRADE team is developing enzymes that enhance fiber properties through targeted introduction of new chemical functionalities. Finally, all these different proteins will be used together for the upgrading of biomass.
The final aim is to actually combine all the enzymes that we use and then expose as much of the hemicellulose and cellulose surface, but maintain some connections, so to maintain a polymer network, as well as having it functionalized. So it's like a synergetic enzymatic cocktail that we are planning to apply on our biomass in the end.
BioUPGRADE's vision is to ensure the sustainability of processes we use to manufacture renewable bio-based materials. The team in Sweden is working on the end application for these technologies.
We are envisioning application demonstrators. Areas that are very relevant. One is textiles, a very huge application area. The second one is health and personal care. And the third one is conductive inks for the electronic sector.
For industry, these new enzymes and expansins offer many benefits.
Of course, we are trying to minimize the energy consumption, for example, so lower temperatures, protein dosage, pulp consistency. There is a lot of optimization to do. And then the most important thing to understand that, okay, what does our protein do in the structure and how we can take the most benefit out of it.
Developing and commercializing these next-generation biomaterials will require the combined efforts of scientists and industry that operate at different scales, as well as multidisciplinary collaboration to leverage the power of biology in catalyzing a genuinely sustainable circular bioeconomy.
What is rewarding for me working within BioUPGRADE is working with groups that have very different expertise from our own.
I think this consortium actually from the beginning, I would say a dream team, because we have fantastic competencies from the genomic side to the enzyme material side and the product in the end, to really create this shift on the way we use biomass materials for high-end applications.
What I see as unique about the BioUPGRADE project is we've come to an alignment of scales, an understanding of what is possible for enzyme discovery, what scale of protein production can we do at the discovery stage, and how can we characterize our materials that align with those initial limitations.
The fascinating world of biocatalysts and enzymes holds vast potential in replacing intensive manufacturing processes and petrochemicals, while promoting sustainability and preserving our precious natural resources.